that one of our honorable MDP. Green welcome to. Ladies and gentlemen, it's my privilege to introduce Mr. Rajkumar Soni to you. He is BTech in Electronics and Communication Engineering, and he has got work experience in the industries for about 17 years in the domain of power electronics product development. Currently, he is working in L&T Technology Services as with the designation of Technical Architect, and his main role there is Technical Project Manager and Industrial Domains, and he is earned reputation among all ranks in L&T for his technical guidance to his team. Ladies and gentlemen, please put your hands together for Mr. Rajkumar Soni. Thank you, sir. And it's my pleasure to be here. I got this opportunity to introduce myself in front of you and just to present something here. So basically, I think from 5th February started sessions. So it is basically about the industry standard 4.0, 5.0. That was the main objective behind that, which is how to drive the green technology, sustainability, green technology. And regarding this industry standards 4.0 and 5.0, many majority of the things you have already learned from the previous sessions and on. Here, today's objectives are basically what are the rules of power electronics in driving this sustainability in green technology. So that is what you would see few things over there. And here, instead of the presentations, the majority of the things I would like to have some interactive sessions. Right, so it will be better to have a better understandability from other sides. Yeah. So. Power electronics has a broad, vast area to cover most of the applications in today's era. In terms of this green technology, as we are seeing, there are a number of innovations are ongoing in the market to reduce the carbon contents from the environment. So, moving ahead from this, the sustainability driven by the power electronics for green technology. So, there are a few contents what probably we are about to discuss here. The highlights are, we'll see a very brief of introduction industry 4.0 and 5.0, what is this basically and what are the involves. Power electronics applications area, we'll see what are the areas where this power electronics plays its main role, a vast role. Then, as a part of this these applications only, there are number of applications. Out of them we cover one section, that is transportation, and out of the transportation only in automotive, that is somewhere nowadays it's giving its EV electrical vehicle. So there we'll see some EV architecture is still very big, because we'll see that in later phase we'll see some designs also. What could be the design goals during the designing these things? What are the target to be fixed, and the challenges, type of the challenges, whatever comes, then how to take over those things. We'll see there are as a designer we see in the complete product development, in the complete electronics, there are the number of sections, number of control systems are there. We'll discuss about the majority or main or significant components. What are important in power converters? So that is why we'll say it's main components we'll see in power converters. We'll also discuss about the power converters like AC to DC converters and DC to DC converters. What are the in terms of the technology wise, in terms of the components, semiconductor components, we'll see what are the basic differences among those the components in terms of the technology wise. For example, like silicon carbide, and gallium nitride, it's background semiconductor components. Out of DC-DC converter, we'll see one EV charger. So EV charger, anyways, it could be DC-DC and AC to DC both. So we'll discuss later phase what are there, how to design those. Design goals we will see. So specifically, as we see, whenever any charger we are talking about, so there are some power converters are utilized inside of that. So in fact, there are a number of many topologies are there as a power converter when we see as a DC to DC converter. So out of those which are very useful and which are running nowadays in the designs, we discuss on those. For example, we say there's a half-bridge converter, full-bridge converter, forward converters, fly-mode converters, and the most useful topology that is nowadays running is the dual active-bridge converter, DAC what we call it as. So nowadays this is the topology what is being used in basically in EV chargers. And in the last but not least, that is we discuss on some practical challenges also what we face basically during the designs. So these are few contents what we are going to cover in today's discussions. So we can start with the sessions. So industry standards, we are naming it as industry standards 4.0, 5.0. I think you are well aware, you would have been well aware with these standards as far as the previous sessions covered. So in our traditional designs, there were a number of things which were done, but there were some drawbacks, right, in terms of which probably there might be size constraints, there could be the things which have not been taken care from environmental point of view. So these were during our previous designs. All those have been overcome in the successive way by naming this industry standard 4.0 and 5.0. So 4.0 means somewhere it is also related with the controllability. Controllability means we have number of manual controls. Right? We go and say something, then only it gets said. These standards are saying that where we can have some automations. Automations can happen even in the connections mode also, but in by introducing some wireless techniques as well. So what we call some IoTs and all is coming, right? IoTs is nothing but the systems are connected with some internets, and automatically it has been scheduled to have a set of multiple setups. That is the basically industry standard 4.0. And coming next has been manual activities have been replaced by robotics. So that is another advancement to industry standards for 4.0. Is it working? See, as discussed here, there are a number of areas where this power electronics plays its role. In fact, we can say without this power electronic, we cannot find any area, any sector where this is not available. So even see, just a bit technically we can say electronics and power electronics are there, right? So power electronics is a part of some electronics. So electronics is basically we see as a controllable part, which deals with the low power and low power things. Even that is also there is also power. That we call it power electronics, but it's more and more towards the controller with the less that deals with the less power. Somewhere we can say 5 watt, 10 watts like that things. There it is electronics. As long as we move towards this more than 50 watts or 100 watts, then power electronics will start falling in. So for that power electronics section, there is absolutely a number of things are there which has been used and we will look into. Now, if we coming towards the multiple areas of the applications of this power electronics, that is one is the industry automation processes. We see industrial applications. There are a number of manufacturing lines are there in the industries, right? How does it run? Basically, this is just for example. Suppose this is one. We take one example for this mobile, right? Or some any other equipment which are to be manufactured. What would you expect? How long does it take to get it produced a single piece? I don't know. It may be hardly 10 to 20 minutes, 30 minutes. That much time only it takes in manufacturing line. This is how it is just because of this automations and because of this industry standards. There are a number of automatic equipments are being used for manufacturing lines so that the producibility are to be improved. So, sort of industries, if you see, this is somewhere, one circle is made, it has been categorized. We can indicate, anyways, these sections are there. So we can say just right more sides industries mentioned. So those are few sections are mentioned for the industrial applications like rolling mills, elevators, farms, current mills, construction machinery. These all are for industrial where industrial applications are there. Renewable energy, out of the renewable energy, that is one example. Solar system is there nowadays. That is also, in fact, the coming future may be for the solar things only. The majority of the inputs will be taken from solar panels. Another is the power electronics applications. It is the defense and aerospace too much. Whatever the power converters are there, we are seeing the flights and all, but internally there is nothing but solve the game of power electronics. In terms of DC-DC converters and inverters are there. So we can few examples from defense and aerospace are satellites, space shuttles, aircraft. From utility systems, smart grids, packs, HVDC transmission lines. We know HVDC transmission lines, right? HVDC transmission line, as we see, transmission lines, distribution lines are there. That is AC voltage, right? Single phase is what we see. Most of the countries now move towards this HVDC transmission line. It's a very, very important thing, and there are few state or area where this HVDC transmission line has been evolved in our India country also, but it's not so much. Basically, the vision is that these single phase or three phase distribution lines what we are getting right now at our home, this might be converted into DC lines. So that is what the technology is running behind this. So there is also nothing but power electronics only. These such sort of megawatt, gigawatts power are going to be done. So that is why using this power electronics converters only. We'll see some structures behind it, how does it run. It's a great input voltage. We'll see from design aspects and all. In our daily life also, we see number of applications like vacuum cleaners, UPS, computer, air conditioning, in automotive and tractions, you will see. So there are modern traction systems, shapes, electric power, steering, service, hybrid electric vehicles, and for buildings. Out of all these applications, we would focus towards the automotive area. So as we discussed, there are number of applications of power electronics out of this. There are number of systems are needed to cover at least a bit of each area. But that's why we can have some little bit detail about this transportations applications area. Electrical vehicle. So here also, because of that is to have a discussion more and more on some practical issues, design goals, then design guidelines, different discuss on that. We'll try to get it covered early. Electrical vehicle architecture. So nowadays we are seeing EVs have been introduced in the market now. Instead of this IC engine, IC engines, or they are fuel-based vehicles are there, right? Those are being replaced by EVs. So what is the reason of this? Why is this being done? So this is basically just to make our environment healthy, to reduce the carbon contents from the environment, right? So that is green is where is no emissions of such hazardous components in the environment, right? So to meet the environment target of zero emissions. Is it okay? Is it audible? Yes, sir. Someone is saying not audible. Hello. So objective is to have zero emissions. That is the key objective of bringing the EVs in the market. Emissions have to be nullified from the market, from the environment. That is one. And two, regenerate the ecosystem. That is another objective. Instead of only consuming the things, there are some methodology all that if in case of not getting used, we should be able to regenerate it and get it back to the grid or the source. So EVs must be sustainable for society, and that will be achieved by the EV architecture. That is one. And in EVs, there are the two things. One is the what we call drivetrain, and there is another thing is powertrain is there, right? So drivetrain is nothing but that enables to move the wheels in the vehicles. That is the drivetrain part. And in powertrain, in fact, drivetrain is the part of powertrain. Yeah. So moving ahead with this drivetrain, it's basically the group of components that drive the wheels. Yeah. And powertrain jointly it consists of both drivetrain as well as the engine. applications, what is being given. So both types of motors are being used there. So that is the power of part of powertrain along with the engine. In fact, nowadays in the EVs, instead of engine, there are most of the things are motor-driven things are there, right? Initially, when it was with the fuel-driven vehicles, so it was with the engine. Anyway, and powertrain is always it's available in both cases, either that is EV or some fuel-based vehicles. Types of EVs. Mostly the types of EVs we can say hybrid electric vehicles, plug-in, hybrid electric vehicles, PHEV, and BEVs, that is battery electric vehicles. Battery electric vehicle is purely electric vehicle, we can say. Others are hybrid one. Hybrid means it will have the both options to be driven, right? One is that could be fuel based or somewhere gasoline based, that could be driven by some gases. And electric vehicle is purely there is a battery, no other options to be driven there. So if you see this hybrid electric vehicles, this is being classified into three different versions. That is of series type, parallel hybrid vehicle, and series parallel hybrid vehicles. So just a brief, we can say. An architecture is shown just on the right side. So there is a battery, and then it's driving. Meanwhile, there is an inverter part which will drive electric motor. And another section is just on the top side, that is the gasoline engine is there. So that's what it's hybrid, what we call it as a hybrid electric vehicles. Series hybrid vehicles. In series hybrid vehicles, see just some just for understanding a few flow diagram or architecture that is shown here. On the left side there is the engine, and then there is a transmissions. Transmissions are there, and out of that transmission there is the inverter, and inverter is having the input from both. One is from transmission line, and another is from the battery, and then it is fed to the motor or generator. The generator would be another inverter only, and then drives the wheels. In parallel, if we go to for these parallel EVs, in parallel HEVs, directly from this transmission, it will go to the wheel, and another is directly coming from this inverter side that drives the motor and wheel directly. So both are in parallel. And series parallel would be in combination of both. It will have the options to be driven, means a generator will be driven by this transmission line, and then it goes to the inverter, and in parallel also that will come to the wheel. So series and parallel both combinations are there. Plug-in hybrid vehicles, see, it's basically use batteries to power an electric motor as well as another fuel such as gasoline or diesel to power an internal combustion engine or other propulsion sources are there. So basically, this PHEVs usually have 32 to 60% less petroleum than conventional vehicles. Anyway, it's a hybrid, so that's why petroleum things are also discussed here. Batteries, this is basically the main EVs, what we call, there is only one source, that is the battery base is there. And it's run only on battery charge, and it has less component in its architecture. Of course, there are components are also being reduced. Only the drawback is there nowadays. Battery is occupying a bit more space in overall vehicles. This is this image is showing actually the multiple sections of or different sections of EV's architecture. What are sections are there? Some rear drive motors are there, power steering is there, compression is there, high voltage power distributor is there, inverter is there. So it's just what happens, it's a given. Okay. Now, if you see the main blocks of EV, electric vehicle, that is basically one is the electric motor, battery pack, inverter, charger, DC-DC converter, and some etc. Means there are some control circuits that are there. So these are the key 5 blocks of EV. One more thing, like this electric motor is there. It's a component. To drive this electric motor, there is again power converters are there, inverter are there. They will drive this. Battery pack, this is again a component part. Inverter, it's a power converter. Charger, that is also power converter. And DC-DC converter is again, it's a converter, but probably it could be to drive the control circuit to generate the power supplies. Role of power electronics, new is, okay, from here we see converters, when we see power converters. So power converter may be AC to DC or DC to DC or DC to AC. So based on this conversion, when it is DC to AC, so that equipment is called inverter. Means the equipment which has the DC to AC inversion, that is called inverter. When it is AC to AC, then it is basically AC controller, transformer, cycle converter, these are the different things. And I think we all are familiar with these terminologies. Transformers we know. Transformers and cycle converters, what are the difference between these two? The backside students are there, right? Okay. So anyone from the student side can tell the difference between transformer and cycle converters. Transformer, that is linear transformers. I'm not talking about the high frequency transformers. Anybody from your side? Okay. So transformers, basically, we see it converts only the transformer voltages without changing the frequency. That is the key. If we see the input voltage or primary voltage or secondary voltage, there is the difference of the voltages only. Something has been stepped up or something has been stepped down. But frequency remains the same. 50 Hz input, output is also 50 Hz. That is the transformer, AC controller or transformer you can say. There are multiple names also we see. Cyclo converter is again one equipment. There same purpose will result. Conversion of voltage, whatever the voltage we see with respect to input. You can generate any voltage as per the specified range of in that equipment. Along with the frequency as well. From this cyclo converter we can see we can have 50 Hz, 1 kV, 50 Hz, 400 volt, or 60 Hz, 100 Hz, 120 Hz, whatever. So this is another equipment. But both equipments are dealing with the AC to AC converter only. So this is another type of power converter. So power converter basically this is cyclo converter. This is here the role of power converter, right? This is only it's a gate transformer. It's a magnetic part. Next inversion is a rectifier, and we also too much familiar with this word rectifier that converts AC to DC, right? And again, you would have studied about of type of many varieties of rectifier also, right? Those rectifiers could be uncontrolled and controlled rectifiers, right? Uncontrolled, that is diode based. Controlled, which are basically where we can use the it's again one AC to DC converter is there. Okay, so this is about some brief of before going to a bit detail in designing part of any converter. So we must know what are the converters are there, what are the terminologies being used in power converters. We should also know those. Then only we would be able to analyze the parameters of any power converters, and we will be able to meet those specifications in that. So later phase we will discuss about the terminologies also, which are used in majority in the designs. Here, so out of all those converters, so we'll see here we'll focus towards the two converters. One is the AC to DC and DC to DC. In fact, AC to DC covers everything. DC to DC is the sub part of AC to DC, right? This is a bit broad block diagram of AC to DC conversion. The first phase, input. As we said, it's a AC to DC. So here input will be AC, and AC. Now in India we have this 50 Hz, right? And distribution voltage, if we talk about single phase, it's 220, or if it is 3 phase, then it's 440 volt is there, right? This is another, we have to keep on thinking with respect to the design perspective as well. AC source is there, that is the distribution voltage. In case this input could be grid voltage also. As long as this distribution voltage input is going to be changed to grid voltage, design will have a lot of changes inside of that. So we'll see those impacts. So input is the AC single phase signal, then it is introduced to EMC filter. If we are using, if or even not using this EMC filter, system will be working. EMC filter, as we mentioned, what is the role of this? We'll see its significance, right? In case if we are not using this EMC filter, in that case also your system will be functional. System will be working without any issues. Only the point is that from long-term point of view, that is one, meeting the compliance as per the standard, which should not interrupt to other equipments as well, that we call EMI, emissions standards. This EMC filter has to be introduced. Without that, those compliance cannot be met. So here in EMC filter, in design parts, we will see what are the section of EMC filter. You can treat each block as a control system. Here, we have studied control system in our engineering, right? I think most of you have studied, or someone will study in some coming semesters like that. And the control system has its one input and on output some feedback like that, and then it gives its output as a part of some transfer function like that. So we have to correlate these practical things with respect to that, and that is only that what we design for this industrial applications, right? Next is the rectifier sections. So rectifier sections, as I told, depending upon the applications, power rating, we decide which type of rectification has to be used, whether it should be controlled or uncontrolled, right? So that is one, and this is along with this DC bus capacitors. Why is this being kept? Because it's a main component of rectifier. A very big role is there, so we'll discuss on that also. Next is this PFC, power factor correction circuit is there. This is again whether it is to be used or not. That is again it's as per applications, whether we are about to meet some efficiency part throughout the band of the input band. So this is the band, for example, a power system should work from 90 volt AC to 270 volt AC as a single phase. Okay, on that time we have to see what are the design cares have to be taken in that, so that throughout the time our power systems should be able to deliver the right efficiency, less dissipation, and other controls as well. Okay, so this is another power factor corrections and things. And basically, the power electronics what we evolved it is as a active power factor corrections. Why do we use it? We'll come to that. Because majority of the things already there. Okay. Again, what is the difference between the input of PFC and output of the PFC? Why is this being introduced here? A bit will elaborate here, we can discuss here a bit more again. Rectifier, as long as S input varies on that time, should I use this? Yes. This is just a block. Sources there. Second, I'm just making a PFC section, and then this is being cut here. Do some. In this, if you see this output, we rectify. What will be there and what will be this here? Reduce. In case if it is suppose input is from 90 volt AC to 270 volt AC. What we see, the output of the rectifier will be in proportional to whatever the input values, right? If 90 volt, so it will be 90 root 2. That is the peak voltage will appear here. And if it is 270, then it will be 270. Okay? The objective is that, the point is that here we are getting a wide range of DC voltages, rectified output. Right? What will happen here? PFC output is always constant. Constant we can say. If you see, PFC has been designed for 400 volt. For single phase it is 400 volt DC typically. This may vary from 380 to suppose 410 volt DC. Irrespective of whatever the input, 90 to 70. If input voltage is 90 volt, PFC output will remain 380 or 400 only. If it is 270, still the PFC output will be 380 to 410. And that contributes a lot in getting the efficiency, reducing the losses, and for better controllability. Right? That is the what PFC things. There are other things as well along with this, so we can take a bit early. Next thing we are seeing is a power transformer. What would be this power transformer? Is it linear transformer? At least expecting something from some response from student side. Okay. This transformer is high frequency transformer. It's not linear transformer. Linear transformer, that is, so 50 Hz transformer, 60 Hz transformer, they are the linear transformers, which are big size. After that, after this PFC phase, we are introducing to DC-DC converter phase. Okay, my speed of speaking is okay or something has to be rated bit more speed or less? What is that? See, this block is made here, right? This is the part of DC to DC converter, right? So in DC to DC converter, what occurs, that is that. What this, we are seeing power transformer, after that there is secondary rectifier, and then final output filter, and then it's a feedback. So this feedback will be voltage feedback and current feedback both. We see that is fed to some error amplifier and again some PWM regulator, which will generate PWM outputs to control the gate of power switches. That is then gate driver will be there, and then it will drive the power switches, and then it's being fed back to the transformer. So this is the overall structure of this DC to DC converter, and wherever we see AC to DC, that is being introduced from here to here. So as a takeaway, if we see as a power electronics engineer, what are the areas where we should have the expertise? Then we can say it's a power electronics things. So we have seen here, along with the electronics, one section is this EMC filter. Even this is not a part of power electronics, right? But it is an essential part of that to make it compliant as per some applicable standards, global standards. That is one. So we must know about this, the design of EMC filter, that is one section. Second is the power electronics, what we are calling it power electronics. Means selection of the components, how are these power MOSFETs, IGBTs, tracks anyways it's not being used nowadays. Power MOSFETs and IGBTs are mostly being used. So how are selected these components, right? So power electronic components, MOSFET, apart from the MOSFET there are diodes, right? So those we must know about that, how to select those components as per the requirement. And then third thing is the transformer, and at the output we have seen output filter. As a part of output filter, it's nothing but LC filter, low pass filter. So there is inductor, right? So inductor is here, transformer is here, and as a part of the CMC filter, there are still chokes. If we break this CMC filter, it consists common mode choke and differential choke. So that is another part. So what we are seeing, that is called magnetics. Either we call common mode chokes, inductor, or transformer is all magnetics. So if we summarize the overall section of power electronics, that is itself one power electronics components we should know. Second is the magnetics. These are the two key things. And the associated skills along with this is the thermal management. Whenever who is playing with this power electronics things, dissipation happens without it. Because 100% efficiency is an ideal, right? Always we talk efficiency is 90%, 95% or 85%. Then what about the rest? The rest, which is away from 100%, is the loss. And loss gets reflected in terms of power loss, reflects in terms of what? How do we feel it's lost? We see that in terms of heating. We see loss doesn't, we can't see that, but we can feel. What is that feeling? That is the heating. Heating is only that thing that yeah, something is being lost here. Power is being lost. Not something, it's power only. Right? So, power dissipation, so for this power handling or thermal management, that is another associated skill is that to dissipate the power, how do we dissipate? Absolutely. Some, if it's a high power loss, suppose it's somewhere 10 watts, 50 watts, 100 watts, as long as we move towards the higher power rating of the converters, that losses, if it's 1 megawatt, then they put the losses somewhere in kilowatts, 1 kilowatts, 2 kilowatts, like that losses are there. So handling of this much power losses is a big challenge. Okay? So again, number of methodology, technologies are evolved to handle such a losses. also having its limitations. If you want to dissipate 1 kilowatt of power losses, then we may need a bit high, very big size fixing, which will not be viable to be used as far as the form factor of product is concerned. So on that time we should know what are other methodology, other technology to handle such a power losses. So that could be closed air cooling. What is the natural cooling? What I told only we are mixing is that is we call natural cooling. That methodology is called natural cooling. Second is the forced air cooling, where we use some fans also for cooling that. And still that is also having a limit to some extent. Again, power losses have been increased. Then some liquid cooling does. Okay, chilled coolings are there. Here, the power components are immersed into those liquids, cooling liquids, right? So if we summarize, overall this is what about the power electronics. Whenever we are introducing devices in power electronics design, so we should learn these 4 key areas: power electronics handling, design, selections, magnetics design, out of magnetics design there is a power transformer design, and for power transformer design or any magnetics design will come on a bit later base. Okay, so this section, this block we have seen, right? If you see some traditional designs, so traditionally this was being controlled by hardware components only. Hardware components by using some operational amplifiers as an error amplifier, some PW regulators dedicated its being compared, and then accordingly PW is generated to control the duty cycle. Right? Nothing was there microcontroller. Nowadays, this whole part has been replaced by microcontroller or DSP, FPGA, those are. So the benefit of this is that whenever this thing we are fulfilling about with this hardware components, these were the components counts were more. On PCB, big space was being occupied and size was being impacted. Right? So these many components have been reduced by a single component, that is the microcontroller. DSP or FPGA based things are taken care, and all those controls are involved. This complete duty cycle is being taken care by this microcontroller. This is the latest technology that is being run in the market now. This is again for specific applications zone of DC-DC power converters. Battery, there is where we use for charging, chargers we use, right? Chargers it's a power converter which is used to charge battery, electric vehicles, satellite applications, AC home appliances, photovoltaic array, that is for solar, we see, and fuel cell stack. And again, this is somewhere a brief about all those applications. I think we already discussed on this. Okay, now terminologies. This is very important thing. Without knowing these terminologies, we cannot proceed for any designs. Either we talk, see, power converters, whatever we see, this is nothing but it's a power supply. And power supply is what? Which has its output voltage. And if it is having some energy, then of course it will have its current rating, sourcing current, right? Jointly, this is called power supply. And now this power supply has been now renamed or is being called with different names as per the applications. If that is being used for charger, we started calling it as a charger. Charging purpose, that is being used, we started calling it as a charger. For variable voltage generation with respect to different frequencies, that is cycle converters. So these all are the power supplies only, right? Okay. Coming to the parameters, terminal losses for this power converter. As in the previous slides, we have seen input section and output section, right? So few parameters are there which are just for to define the inputs, and there are parameters to define the outputs as well. So we focus on the input parameters, that is the efficiency. We all know this, right? So output power divided by input power equal to 100%, that is the efficiency. But we should know which type of power we are talking about, whether it is active, reactive, or apparent power, right? Then we will be able to derive it. Okay, so this is we are talking about active powers, right? If that is reactive power or something apparent power, by default whatever we see, which type of power is this? 230 volt AC, and suppose 1 ampere RMS current is being taken, then which power is will get that? What will that? VR. That is apparent power. What is that? Apparent. It's not actual, it's not real. Real is something different, right? When it is being multiplied with the power factor. So after the multiplication of this with power factor, then we will say active power. And this has to be, so this equations and all will happen on the basis of active power supply. So by the formula it states, it is very easy, but to derive it, we should know which power we are talking about. Okay? As a part of AC to DC conversion, see, during explaining all these terminologies, I'm just trying to correlate with the blocks, with the designs, input and output. So please have some imagination and visualizations of those. And wherever any query, can please raise your hand, right? So as a AC to DC conversion, we see here output the AC, but input will be AC. And we, if we straightforward, we are going to that AC output power divided by input power is there, right? Unit should be same, right? So the input power has to multiply with power factor, cos phi, then it is will be very close to the actual efficiency what we are targeting for, right? Power factor. Power factor, by default, we don't use any correction things for the power factor specifically. Any system has somewhere roughly 0.5 to 0.6 power factor. What is the maximum value of power factor? Someone has told 0.8. Is it? Yes. Cos phi is, the max value of cos phi is, right? So it's 1. So in our circuitry, if we have not used any power factor corrections, so typically it is 0.5 or 0.6 by default, right? So to improve it, we use the power factor corrections. So as long as active power factor corrections we use, that is, we target is to bring that closer to 1. Ideally that is not 1, but it's achievable to 0.99, 0.98, that much. What I have done, I've used in our design with all most of the relays. Okay, next is the fuse. This is again a part of input only. This is also a number of, every section has different technologies, not a single thing. We are calling fuse, but this fuse would be that single component we have placed, it's blown out, that's gone. So this fuse has also been used with different sections, like that has been introduced soft start, some PTCs, some electronic fuses. Once blown, it will reset itself. You need not to change it physically when you replace the fuse, right? So these are the options where we can use based on the requirement, applications, and cost need, right? So whenever we are talking about fuse, so we should have the question which type of fuse we are talking about. Whether it's a simple glass fuse physically which is replaceable, or something electronic fuse inputs which is automatically resetable after getting its reset, right? Input current. So we are aware as long as some load has been brought on the output side, so proportionally there some input current will flow as a part of some RMS, right? Input current will be that only. Maximum input over voltage. Here it is over voltage written. It's not voltage written. So what is the maximum input voltage? That I got here, it is maximum input voltage 270. That is the maximum input voltage, operating input voltage. Right? When we talk about this over voltage, so that is if what if the input voltage goes beyond 270? On that time what will happen? Right? Means it needs some protection cells. Right? So another area apart from those what I discussed, power electronics, EMC, magnetics, thermal management. Next section is the protections. Right? One by one, you may, if you want, then you can note down. So another section is introduced, that is the protection. So whenever we are running for any design, so the next thing which should come in the mind of our designer, that is about the protections. What are the type of protections we need to provide? Right? Because any product we are able to make it run for years. When is this possible? When there are protection things have also been taken care. Because the number of situations are there, number of conditions are there, which changes the dynamics, loading conditions, environmental conditions. Anytime anything should happen. So this all should be taken care in the designs. That's what some global standards have been made in the world. Whenever we are designing for a product, then we see this product is lying under this category for this application. So for these applications, what is the relevant standards? IEC standards, EN standards, right? ASSE standards are there. So these are all the standards where we see. So from power supply, for example, this from power converter side, IEC 6038 standard is there, right? From so different sections are there and all standards are there. That is called safety standards. Those have to be followed as per that our design should comply. Okay. So that is the voltage over voltage. Reflected ripple. Reflected ripple. Its output is AC. Right? So ripple we know what is this? The AC contains current in the DC. Input is our AC, input is the AC, and we are getting that AC. And of course, if we say no, zero ripple is there, is it possible? See, 0 and 100% is only the ideal. No 0 is there, and no 100% is there. Everything runs between this only. 100% means if it is, even if it may be 99.9999, but it is not 100%. Similarly, 0 also. It may be 0.00001 something. It's not 0. Right? Similarly, whenever we are seeing for any DC outputs, there will always be few contents of AC. AC, if it is for low frequency, 50 Hz, 100 Hz. Right? At the same time, if this frequency becomes high frequency, say for 100 kHz, 50 kHz, 200 kHz, this is the ripple in the DC. Then that is, on that time this terminology is changed. That is called noise. On that time that is called noise. So that's why ripple and noise both are jointly called. If we say only ripple, it's a low frequency components. If frequency change, then that is called noise, high frequency noise. So their measuring units are also being distinguished. So ripple is being measured in terms of RMS, right? 5 millivolt RMS, 10 millivolt RMS, 1 volt RMS. This is the ripple in that out of 100 volt DC. But if you say what about ripple and noise, means along with high frequency formats as well. On that time, this is categorized in the unit of peak to peak. On that time, we say 5 volt peak to peak, 10 volt peak to peak, 10 millivolt peak to peak. This is noise, ripple and noise we call it. So if we see any data sheet, a specification of a power supply, a power converter, anything, anywhere. So these are all the parameters mentioned there. It's defined there. And these are all the key and important parameters which qualify any power system. Switching frequency. Where it was used? Switching frequency, in the previous slide we have seen transformer, power transformer, right? So this is what input parameter to design transformer. Second, we have seen the feedback, right? Closed loop, that we call as a control. Control, so if we go for a control, so that two types of controls: open control, open loop, and closed loop. Open loop means whatever inputs is being fed, accordingly output is being changed. That is open loop control. Okay? And what about the closed loop? In closed loop, we makes the boundary. Whatever the changes either in the input or in the surrounding input, output should be here only. Okay? And then we do that by using closed loop. Right? This is the set value. And this is what is coming actual value. So very quickly, can that be corrected to bring what is set closer to set? That is the game of closed loop. That is the true closed loop. And how is that closed loop done? Finally, as I mentioned in the previous slide, just it will go back to that. Here, this output, right? PWM. What does this PWM? Just because of PWM, what happens? How do you control that? This is the game of this PWM. How PWM is being controlled by this input, right? And through this PWM we control the duty cycle of that. Duty cycle, for example, if it is 5 volt, we have something load has been applied, it has been changed. It's a natural practice, it's a practical thing, sir. Whenever there is some rope, if something is hanging over that, so there will be the stress over that rope, right? Same thing will happen with this also. If it's a power supply, some load has been applied, and some tendency that it will go down. It means the same voltage will be disturbed, whatever it is, wherever it was. Okay? So that disturbance has to be nullified in a fraction of seconds, fraction of milliseconds, so that user should not be able to recognize some change has happened. Internally, it happens in fraction of milliseconds, nanoseconds, that we are not able to recognize something correction has happened. But internally, it happens and we are able to see, this 5 volt was there, after applying the load also it's 5 volt only. There is no change. Okay? So that is what is being controlled through this duty cycle. And for a duty cycle, it's a signal. So we need frequency. Okay? It's a some frequency has to be there. So what is the point of this frequency? How should it be? If it is low frequency, 50 Hz, 100 Hz. Okay? On that time, what is the meaning? This power converter techniques are high frequencies are not needed. And of course, there should be as high frequency that was useful. But still it is having its boundary. In case, I don't know, in terms of this selection of this switching frequency, this is the key thing. What should be the optimized or very appropriate switching frequency we should select for switching our power MOSFETs, and accordingly our power transformers as well. Okay, if this low frequency on that time conduction losses would be higher, and even the size of the components like transformer inductors and capacitors, electrolytic capacitors, their size will be so big, and it will be very difficult to handle the sizes. One manufacturer is there in the market, that is Day-6. His design is still linear designs, where low frequencies are only being used. Because of that, such a low size of power converters are there. But it's a well-known, it's a well-applicable for the industrial applications. It's too costly and customized. It's being used. It's well known for its precision and accuracies and all. Right? So switching frequency like 10 kilohertz, 100 kilohertz, such type of frequencies are to be used, even not high, because these power components are also having its limitations. How long, how much frequency can they support? The power transformer what we are talking about, its key component is the ferrite. High frequency component is there. When it's power transformers linear, there we use iron cores. We know in transformer there is a core is the thing. Okay? So core could be the material of the core could be iron, CRU or some ferrites high frequency materials. Nanocrystalline, these are the varieties of materials used for making the core. Right? In case of that iron core, it's suited for only 150 Hz, 100 Hz, 120 like that only. So because of that, size of the transformer just for same power rating we are making 1 kilowatt, power transformer is something this much size. But if we convert to high frequency transformer with the ferrite, that could be somewhere this much size. Right? So that is one. During selecting the switching frequency, we should know what are the components we are going to use and what are the limitations for the operating frequencies. Accordingly, we can take the between switching frequency for that. Turn on time is as long as we switch on the power converter. How long does it take to stabilize its output? Right? As long as we have fed the input to the system, and how long will it take to give a stabilized output? That is what it's a turn on time. Under voltage lockout. This is again, we can say it's a part of the protection circuit only. Under voltage lockout. As I mentioned, it's a 90 volt is the minimum input voltage. Okay? Then what if input was less than that? Okay? So somewhere we have to see, because see, at 85 volt it has been there. Output is fully loaded for, suppose it's a 100 kilowatt converter is that. Okay? At 100 kilowatt converter, load has applied at 90 volt, there will be too much space on this section, rectifier sections. Around the input side. If PFC is used, that there may not be too much stress on this side, but too much stress will be on this side. In case of the input is the minimum, right? So if it goes at less than that, again the stress will be keep on increasing, and one scenario will come. This may reach to the threshold of failure, right? So another way we have seen that some protection has to be applied as an under voltage lockout. For example, if it goes somewhere at 89 volt input or 85 volt input, system should get switched off. Switched off means output should be disabled. No load should be taken. Right? So that is what. Voltage bands. Okay, anyways that we discussed and now coming to the output parameters. Output parameters we see regulation word. In our power systems we see majority that how much is the regulation. Regulation is nothing but that is the change in the voltage. Right? As per in power systems, whether that system is being used for EV charging or some to drive some inductive load or some capacitive load or even some resistor load. On that time, this regulation means that system operates in what are the modes are converter, right? CV and CC mode, right? These are the two. This is the two characteristic I've got here. This one and this one. What with this graph, what are we seeing? Here voltage is constant, right? While current is changing. This is 0. From this 0, we have applied the current to the set current to its capacity. Here we are starting from the no load to the full load, voltage is constant. At the same time, if you see the second graph, here voltage is varying, but current is whatever it is set current was there, that is constant. These two are called CV and CC mode, right? So we define it's when we talk about this regulations, so we talk about the regulations in CV and CC mode. What is the voltage regulation in CV mode, and what is the current regulation in CC mode? In CC mode it is current regulation, and in CV mode it is voltage regulation. So when we see for voltage regulation is again things comes with respect to the input. One is that we have set a particular input to 70 volt. Okay? And then we apply the load and we see what is the change in that. Second is that if we change the some load has been applied and we have changed the input voltage from min to max. So again, so this regulation is divided into two parts: load regulation and line regulation. So in load regulation we see only which we keep the input constant, right? And we change only the load. Just for example, suppose here the voltage was 100.00 volt. Okay? This is something 10 ampere. We started applying the load from no load to full load. No load means that is 0. Full load means gradually started increasing from here to here and it reaches to maximum 10 ampere. So from 0 to maximum this voltage be constant. Constant means again it is idle. There will be some changes because its regulation when it is there. Load has been applied, some changes has to happen. Okay? So this voltage may be somewhere. That what we call as a regulation. It is 5 millivolt or 10 millivolt. And suppose there is a change of 10 millivolt. Out of this 100 volts. Okay? So that we call its load regulation in CV mode is 10 millivolt. Means when we have started changing from 0 to full load, there has been seen a maximum of 10 millivolt variations only in the output. input voltage from 90 to max 270, whatever it is, and we see is there any change in the output voltage? Some change will happen, something 5 mV, 10 mV, that is called high condition. We define that. Right? Coming to this CC mode current regulation. We are talking about this battery charger, right? Usually, if we see the equivalent component of a battery, what is that in our as a part of passive components in electronics? Capacitor, right? Capacitor bank is something is equivalent of battery. What if charge capacitor is there and a discharge capacitor is there? If we have applied a DC voltage across that, so what is the instantaneous characteristic? This is a capacitor, right? Some DC voltage has to be applied here. We have provided one switch, right? This is what Day-6 use. This capacitor is the equivalent component of a battery. We are saying when a battery is fully charged and when battery is fully or partial charged, and when in case when battery is fully discharged, and on that time, if we connect a charger or system, then what are the things happen during that? If we are able to characterize this capacitor characteristics, so this instantaneous characteristic of battery could be analyzed, right? So as a part of this instantaneous behavior of capacitor, we have seen we studied this network analysis. We have studied, right? So in network analysis, in network analysis, we see how does this what is the instantaneous behavior of at t equal to 0, what does it be, what will it be, and what is t equal to something plus like that, right? So at t equal to 0, if it is fully discharged, capacitor is fully discharged, as long as we have connected the supply, DC supply, this will act as a short circuit. Short circuit I mean the minimal resistance. Only practically whatever the ESR of the capacitor is there, that will only come in the picture. Right? The instantaneous characteristic of this is a short circuit. Means whichever the charger we are connecting, and see it's a very critical thing. As a general, if short circuit happens, then what happens? What happens as a result of short circuit of any power system? In short circuit, what happens? Infinite amount of current will flow. If a system is having the capacity to source 1000 amps of the current, there is no control. If that has been terminals have been shorted, no amount of current will flow. And whatever path is there to flow that current, that will be once out in case if it is not rated for that. Right? Same case here. This is the charger. Instantly, as long as it is connected, it will act as a short circuit or the minimum resistance will be provided across the load. If this DC charger source is not protected against short circuit, system will also be damaged and this also be there, because this is somewhere it's rated for few specified current value, not infinite amount of current. So that will also be increased and this is also damaged. So short circuit protection is also needed. So short circuit protection against which current? That's what we are talking about. CC. Constant current we are seeing. So whenever we see any power system, so we'll see that it's written there. It is written, it's for 10 ampere, 15 ampere, 100 amps, 200 amps, right? This rating is there. So that is basically it's constant current. As long as the system reaches to constant current, and over that also still we are trying to or take the load. Then what will happen? Now coming to back this here. In CV mode, it has reached to its maximum current rating, right? From 0 to max current we have applied to load here, right? What if later to this also we have applied to load? Then we can keep on applying the load, we have reached to the maximum capacity of the current, right? And after that again we are still continuing to apply the load. What will happen? This will start like this, right? Means as long as it has reached to its maximum set current, it will start. It means what? Output voltage. Output voltage will start going down as long as load is being short circuited. At the short circuit, this output voltage will become 0. And this is what CV and CC mode. It's a very, very important protections, controls of a power system in the CV and CC mode. Whenever we are talking or discussing about a power system, then we must know what are these, where are these, right? Okay, so now this current calculation. In current calculation, what it is? This threshold I told, right? This was set at 10.0000 amps. Still we are increasing the load. So will this voltage be 10.00 here? There will be some change in that. Might be 10.00. So maybe from here to here, this set current may be varied from 10.00010. During the maximum current, it was 10.00. But when we have continued to go towards moving the short circuit, it has become set current has been 10.010. It's a 10 milliampere variation. So this 10 milliampere variation is called CC mode current regulation, load regulation. CC mode current load regulation, right? Okay. So we have seen load line regulations and dynamic response. Cross regulations, right? Cross regulation. In cross regulations, flyback converters we have seen, right? The beauty of flyback converter is what? Don't know whether it will be visible here or not. It's out of all power converters topologies, whatever we know, whether that is forward converter, half-bridge converter, full-bridge converter, DAV, or push-pull converters, or NPC, or any other converters, and then flyback. Flyback converter is one converter which is having the facility to provide the multiple outputs, which are called multiple outputs. We can take at a time 2, 3, 4, 500, 550, whatever. This many outputs can be taken, right? So this cross regulation basically comes for when those are multiple outputs are there, right? On that time, some load has been applied to this. Then what about the regulation impact on this? Some impact will be on this. So the impact of one output due to the load applied to that one on others output is the cross regulation. switch to this winding also. Because control is a single, a common control is there as a master winding in private there is a single control. It's as while the controls of the single one, it's all being outputted here. Load is being applied to one, there will be a big impact on the others. That is the cross regulation, which should be ideally zero. Cross regulation ideally should be zero. If it is zero, then we say yeah, it's a very good design, right? But normally a big impact is there in private. Okay, so that is for cross regulation. Long-term stability. Long-term stability, we say, suppose a power system, we have kept it, we have connected some load, some inductive load or even charger also or some any other load. We are observing its voltage, right? We have left it for next 2 days. Okay, so we see where we have left it and what is the status of that output voltage after 2 days. We have set it somewhere around at 100.000 volt, right? Now after 2 days, is there any change? Even if nothing has been changed, constant environmental conditions, constant load conditions, constant all peripherals are constant, but still there is some change at output. That is called stability. So stability will be for voltage as well as current, right? And even on thermal also, we see for temperature thermal stability also. We check for its performance by keeping that power system in some thermal environment. Then we see, we observe its performance if the thermal ambient temperature is changed. So this is all the robust, for a robust design, these parameters will look into the design whenever we are going for a design. So being a power electronics engineer, we must know, we must analyze all these things. Then we can go in the broad, we can keep a step for power electronics design. Okay, this is somewhere maximum allowed voltage between the pins. Some we use connectors also for the interfaces. We should know whatever the connectors we are using for interfaces between the two boards or two signals. So what is the capacity of those pins? Noise we have even discussed. Over voltage current, that is also we have discussed. Rated current, that is we discussed. Short circuit protection we have discussed. Short term stability, that is also is about that is somewhere. Warm-up condition what we see when a system has been powered up, so it takes a bit time to get stabilized to its normal condition. So nowadays it's very fast, only 10 or 15 minutes. For that much time we should leave and then we can start using that. On that time there will not be any deviation in its performance. Just like this laptop in PCs, usually when it is with STD only, it was taking too much time to get it on, right? We have posed on it waiting for a few minutes, 2 minutes, 5 minutes, then it was getting on. As long as the SSD has been introduced in this, just hardly 5 seconds is become ready. It's like that. Temperature coefficient. So temperature coefficient is nothing but whenever this power system has been exposed in a thermal environment from wind. For example, power system has been designed within the operating temperature band of minus 40 degrees Celsius to 70 degrees Celsius. This is the operating temperature band. So first thing is that this has to be validated during the design. This has to be validated for this operating band of the temperature. Even during the selection of the component, we must see whether all those used components are complying with this band or not. Right? This is the key criteria. That is one. Second is we do the VOC. That is, we apply the maximum stress. If we are crossing the limits of the 70 degrees Celsius, moving ahead, then what will happen? Then another protection comes that we call over temperature protection or thermal protection. So that is what thermal protection has to be made. Right? And we provide the stability. So this stability is given for voltage and current. In our design, where we use for current measurement, for current controls and all, we use current sensor. the stability of that resistor. How is the resistor selected? What is the resistor parameter? You know resistor, transistors, this, so there are few parameters and the capacitors. So for resistors, what are the key parameters what we can see for the resistor? Anybody want to say something there? Initially only I said it's interacting, it's not presentation, it's just fine. Something else to be recorded for its presentation, otherwise I was not looking over this presentation also. It's a better, we can have an interacting session, so no question and answers, right? Anyone from student side? It's a key components. Okay. By the way, which semester is running of yours on student side? Third semester. Third semester means everyone has been introduced in their area, right? Specific to their branches. Right? So resistance, you should say it's a resistance value. What is the resistance value? Second is the power rating of the resistor. Third is its stability. Stability is that whenever a resistor has been used, if we are using this as a current sense resistor means current is going to be passed through that, given that is 100 amps. So we have to see after flowing of that current from 100 milliampere to 100 amps, what will be the potential difference will develop across that, and how will that be measured? So on that time, one is the value will come, and second is the power rating. If 100 amps goes through a 1 ohm of current sense resistor, what will the power? What will the power? I square, right? So means the current sense resistors what we are selecting, that its rating should be more than so much, at least 20-30% higher than that what is required, right? So which point is that resistor where are we using? For which purpose? Whether it's being for as a differential divider or for current sense applications or for something else. So that is for stability thing. Transient response. Transient response again, as I mentioned, there is a road, a person is hanging over that as a road. There is some data in that. As long as if he leaves that rope, so there is an oscillations and rope will go something for a moment, goes up and then it settles down. Right? Yes. This is one characteristic I have drawn here. This is the load characteristic. Here it is. These things are shown here for load applied. Sorry. Here it is. This is load applied. This is voltage waveform. Okay? This is the voltage waveform. When load is applied, so suddenly that wave will come here. Okay? And again it will get recovered in this much time. This time is going to be somewhere 100 microseconds or 1 millisecond. condition, the load is applied within a fraction of a millisecond, it gets battered and fixed, and users are not able to recognize whether some changes happened or not. This is that load is applied, suddenly a dip comes in the output voltage, and again it gets recovered and stabilized. This is the duration, and that duration goes around 100 microseconds or 1 millisecond. In this much short period of time, closed loop has to take care of to correct those changes in the voltages and get it corrected. Right? So this is when load is applied. In the same way, when load is removed, on that time this happens. Suddenly, as long as load is removed, the voltage will get shoot up for a shorter time, and again it gets stabilized. Right? So this is again somewhere to the point of 100 microseconds or 1 millisecond, and this has to be recovered in this much time only. That is called recovery time, transient response time. Dynamic conditions, load changes anytime, load is getting less, high, right? Something no load, full load, something changes, short circuit is, these things are the dynamic conditions. So during all these conditions, the control loop should take care of that. In terms of this battery charging, there is called one thing BMS, battery management system, where as a part of control loop that takes care of all these things. With respect to the healthiness of health of battery, where we see state of charge, state of voltage, and other things. How much is the battery charge is left, how much is to be, all these things are taken care of there. Okay, this is this transient voltage balance is there, voltage range, case specification, storage temperature is there. Operating temperature is different and storage temperature is different. Where is the system or product is going to be stored, that temperature should be a bit high. Okay, so that is one, it's specified for that. So these all parameters are given so that the designer should take care of all these things during his designs, during the selections of the components and all. Thermal impedance, thermal resistance, everybody knows this. One thing what we mentioned about this thermal management, heat sinking and all. So this is the characteristic of that. This is the thermal impedance on the, with respect to which input we decide the heat sink area. How much heat sink area is needed to dissipate X watts of power. So its units will be degrees Celsius per watt. So this thermal impedance or thermal resistance is specified in the data sheet of each and every component. Whatever components you see, either MOSFETs or diodes or anything, there it is defined. Thermal shutdown. This is the part of thermal protections. We say when temperature goes at that temperature, suppose its operating temperature is 70 degrees Celsius, right? Temperature goes as long as the 70 degrees Celsius crosses, then what action has to be taken or who should be disabled? That is thermal shutdown. Okay? When temperature is below a certain threshold, then output should get disabled. That is thermal shutdown. Right? Okay. Now coming to the key points of scanners. DC-DC converters. These are firstly it's categorized into two parts. One is a non-isolated DC to DC converter and isolated DC to DC converters. Non-isolated means where we don't use transformers, right? It's on the same reference their design runs. Okay, but non-isolated converters have their very limited applications and they can be used. Limited applications means those areas should be to supply the control circuitry, less powers like that, which are working on the same reference. Same reference means same ground. We understand, electrically understand ground, right? So non-isolated is buck converter, boost converter, buck boost converter. These are non-isolated converters. In isolated converters, where we use transformers to separate the primary reference and secondary reference. As long as we are moving towards these isolated converters, switching techniques. Which switching techniques we use? So there are two switching techniques: short switching and hard switching. Short switching and hard switching. So traditionally it was hard switching only. In fact, right now also it's being used in some places based on the power applications, right? Short switching nowadays this is highly being used. What are their differences? Key differences between these two? Just in the previous slide we mentioned about switching frequency, right? Which switching frequency we should use? As I told that yes, as the higher switching frequency, that much is the benefit. But does it mean we should use 10 megahertz? Right? If there are, so secondly I said we should see the compliance of the components. What is the supporting band of those components? Okay. So during the hard switching, losses. If we are coming just we covered about the types of losses with because of these power electronic components as well as the magnetics. The two losses are there. One is that conduction losses and switching losses. Right? So during the conduction losses, frequency doesn't play any role. It's straightforward. But as long as we are going for switching losses, on that time, as high switching frequency, that much is the losses. So that makes the limitations of boundary to use high frequency in hard switching. High frequency, if you want to use somewhere 1 megahertz frequency, we cannot use. Otherwise, switching losses will be that much high that it will dominate complete efficiency of the converter.
Is it closely related to SMPs?
Yeah, it's SMPs also. I told that this is all our power supplies. All our power supplies. Under the technique, the SMPs only. Switching mode power supplies. Right? So this is all about that only. So to overcome this switching losses, soft switching has been introduced. Point is that in hard switching, just graph is there. This is. If we see the graph, in hard switching and soft switching graphs are mentioned here. As a configuration of this H-based or full-based converters, we see diagonally those switches has to be on at a time and then second has to be on in during the transition. Right? So during the transition phase, suppose one switch has been on where voltage has not been zero. Okay. It is gone not zero, but there is some substantial voltage, and still there is some proportional current is there. So that V and I makes the switching losses on that. At the transition point. Transition point means this point. This point. This point. Where this V and I is having few values, right? And it contributes as a switching loss. During the switching losses, soft switching, in soft switching, it is ensured when one switch has to be off, then another has to be switching on. Another has to be on. This is done in soft switching technique. But the point, in hard switching, actually there is no way to see that if one has been fully off, then another has to be on. Right? Because during the transition in win-win situation, one is getting on, another is getting off. So in this point, some V and I factory values are there and it reflects in terms of losses. Right? In soft switching, this is only taken here. Another switch, another combination of the switches will be on only and only when previous one has been fully off. So out of V and I, if one is zero, obviously the product will be zero. So then the switching losses are zero. And that's why where we can use a high switching frequency. That's why nowadays this sharp switching techniques are used in SRT. So coming back to this slide. So out of hard switching, these are all the converters are there. Flyback, forward, push-pull, half-bridge and full-bridge converters. In soft switching, there are resonant converters are there, which are even series parallel or phase shifting full-bridge converter, which we also call synchronous converters. DAB, dual active bridge converters are there. In this, as I mentioned, to ensure fully off and full, then on. Those techniques are called ZVS and ZCS, zero voltage switching or zero current switching. Means one out of V and I, one has to be made zero. That is the objective in the soft switching. To get zero switching losses. This is the part which comes in the soft switching. And that is why nowadays, instead of discrete hardware components, only microcontrollers or DSP or FPGA techniques are being used as a closed loop for a control for the control techniques. One thing. This one, MMC is mentioned here. A separate thing, it's there. Just in the starting of the slides during AC to DC power converter, I mentioned if input voltage is other than distribution voltage, that is grid voltage, 11 kV, 22 kV, 25 kV, 25 kV, on that is what? On that case, this modular multi-level converters are used. MMC is used. This is again one type of power converter.
Is it possible to use PID controller?
PID controller is basically, that is anyway, it's a part of microcontrollers. And PID is the basically mostly used in simulations, right? When we are seeing flex or MATLAB simulations we see, there PID is all being used there, right? Proportional integration and these derivatives, proportions. That is that there. But anyway, it's being it's mostly comes under simulations, what PID and PID. But when we are going to execute during this controller on the code levels, same has to be implemented there. This we have discussed. Parts of DC-DC power converters, this we have already discussed, right? Power electronics components, control electronics. What are the control electronics? Mention that is gate drivers. See, these are very key areas. Gate drivers. It's another challenge to select a suitable gate drivers. We should see that how can it be used, right? Microcontrollers, op-amps, digital components, these all are the part of control electronics. Magnetics, anyways, we have discussed. Isolators. Isolators are also the part of that. So those isolators could be opto or some magnetics also. So as a magnetics we say, there is a transformer which is used for the isolation purpose, that is called pulse transformer. Okay, so pulse transformer is to transfer the signal by isolating input and output, but only signal, not all signals. It's a control signals. This is the thing based on the technologies of the components. As we mentioned that we can use 1 megahertz, we can use 10 megahertz, 500 kilohertz. So components should also comply some things. Based on that, technologies also has moved out. Done a lot of innovations on that. So initially it was the silicon-based semiconductors, specifically diode and MOSFETs, modified MOSFETs and IGBTs. They were having their limitations in terms of the maximum drain voltage for IGBT or MOSFET. It was 6.5 kV only. Right now also it's there only. So somewhere this SIC has been introduced where this level has been increased. Nowadays, so it's coming around 10 kV, 11 kV, matching like that. And third is the GAN. The majority of the key difference is the band gap energy. For GAN, band gap energy is more in fact it's somewhere 3.5 electron volt for GAN. Somewhere in 3 it's for SiC and less than 3 it's for silicon. We studied as a property of semiconductors in our durable engineering. Yeah, so how much energy needed to switch the electron from one level to another level, that is the electron volt. That is the key things here to differentiate the things, right? So, if you see this graph, it's in the boundaries of for using this GAN, SiC and application is there, right? And power is somewhere 100 kilowatts. Then we can use with this SI components can be used. If switching frequency is crossing somewhere 100 kilohertz onwards, then we can go for SIC or CAN. And even for this range of the power converter, means power rating, SIC is mostly used. CAN is nowadays CAN is very less under the use because it's right now still being evolved. This GAN is basically, I think it's being used by some defense and space means resource people, but still it's very limited. Not too much being used. It's not too much being commercially available in the market. Okay, but SIC is mostly being used now. For high power converters, SIC is mostly being used. And GAN is anyways, it's too much costly also. It doesn't meet the requirement and so on. That is another limitation. It's very EV chargers. On this, you will see the type of EV chargers. Two chargers are there: on-board charger and off-board chargers. I think this terminology everyone is familiar. On-board charger, which are still equipped with the vehicles already, right? So to charge that something from outside, it has to be plugged in and get charged. AC has to be plugged, right? For off-board charger, only battery is inside. Total like of fuel stations are there, right? Similar, there are the charging stations. On there, charger things are there as a part of charging infrastructure of the station, charging stations. And their output of the charging station will be DC, right? And the DC will directly be fed to the vehicles to charge the battery. That is an off-board charger. That we are calling off-board charger. Off-board chargers would be starting from 50 kilowatt onwards to whatever the band it wants to cover, whether 10 vehicles at a time, 20 vehicles at a time, along with the according to regulations, right? On-board chargers, it always equipped on the inside of that, and the input to the vehicles will be AC, right? So internally it is AC to DC converter, and that will charge the wheels, right? So as a part of this charger, this technique is normally being used dual active bus converters with ZBS, soft switching techniques only, and full bus, phase shifted full bus converter. We don't have too much time on this, more on this. These are the design rules where what is our requirement, right? Where we want to see maximum performance. If maximum performance is the key objective, then we can see only during the selection we can see a component is being costly, also it's fine, right? Applications suiting meeting our requirement, that is also fine. Maximum performance is the key objective. Then technology, what we can use and what are the challenges we can face. Maximum power density. If maximum power density is the key objective, that in such a form factor, this much size of the product, we have to cover too much good power density we have to deliver. Then on that side we have to see, then these are the main challenges. Thermal. If product size is very small, like that, on that time this much heating is there, then how to dissipate that? Some area has to be provided. So these are the key challenges. Similarly for minimum cost, we want such a big specification but with minimum cost. So somewhere compromise has to be made, right? This is just highlights of converters. This is half bridge converter, and this is full bridge converter. Can anyone let me know what is the difference between this half bridge and full bridge? This is half bridge. This is full bridge. See, here some transformer primary is there, right? This is connected. This is how. Here we are seeing it's connected here. Here there are the two switches only. One leg is for this capacitors. Center is there. So what are we seeing here? This junction A. How much voltage will go in here? Here the input is coming 400 volt. So at this junction point, the voltage will be halved. This is the capacitor divider, capacitive voltage divider, right? So here voltage is being halved. That is why this is called half distributor. This is being halved, and this voltage will remain the same. So here basically at the half of the voltage, this is being switched, and controls are being done. So it's half base. As long as we are moving here, this is full base. Here always there will be the full voltage only. 400 volt is being fed here, right? So at the primary winding of this transformer, there will be the full voltage only. That is 400. No half will be there. That's why we are calling it full base. And 4 switches have been used in the form of phases. The key difference between that and this is the full voltage. Full voltage I mean equivalent to the input whatever is fed. That is at the across the primary winding, and in half base it will be half of that. That is one. Second, in full second would be in terms of this duty cycle also, right? Duty cycle anyways on secondary side it can be used up to 90%. Either that is in half base or in full base both. But thing is that we should think then what are they used, which can be used half base or full base, right? In fact, here voltage is being halved for half base. Then transformer size is going to be then to deliver that much amount of voltage and power. Transformer size has to be maximized, has to be optimized according to that. Okay, so it's better to use full base so that the optimum size has to be taken. And second is the dependency of the power rating, how much power capacity we have intended to deliver, right? This is DAV, dual active bridge converters, which I mentioned. Normally this is not being used in EV charger as a part of EV charger. This is comprising this LLC and all techniques. The key things in this DAV is this. One series inductor we are seeing right in the transformer. This series inductor is nothing but it's a leakage inductor of the transformer. This would be, if this value is possible to be integrated with the transformer itself. We know whenever we design any transformer, leakage inductance itself is characteristic. That will come according to that. Zero leakage inductance is an ideal state. 100% there will be some leakage inductance. We know how to measure leakage inductance in transformer. For a transformer, you want to measure its leakage inductance. How do we measure? Simple. Make secondary is a short circuit and connect LCR meter across the primary. So whatever the inductance you get, that is the leakage inductance of transformer. Right? So usually this is time that this leakage inductance in DAV, what I am saying, this has to be associated with this only. In case this is something higher value, then one separate inductor has to be connected in the series of this. Second thing, the whole role of transferring the power from primary to secondary is this leakage inductor. So this has to be very carefully has to be designed. Its value, right? This one. Second, we are calling it DAV, dual active bridge. So we are seeing the same switches, same bridges are there. Whatever is primary, same is in secondary. That's why it's called dual active bridge. Dual, there are two bridges, same similar type of that. Right? Third point is the primary and secondary voltage ratio. That has to be seen. Then only Z is what are we calling zero voltage switching. That must be seen. Means suppose if there is the 400 volt is there across this primary, then 400 volt has to be there across secondary also. Then only ZVS criteria will emerge and it will be able to be verify the switching losses. And for the power transfer, this leakage inductance is the main contributor. Right? So that is what. So just because this is anyways we have discussed private converters. Flyback converters. Anyways, partially we have already discussed it. This is one beauty of this power converter is that there may be multiple windings, multiple outputs can be taken from this. And this is one converter which is used to create the control supply voltages to supply our control circuitry, like op amps and all related 5 volt, 12 volt, 15 volt, such sort of power supplies with the current capacity of 1 ampere, 500 milliamps, like that. This converter is only used. And this is the standard structure of this. Second, what are we seeing? It's flyback. If you see the from functional point of view, we are calling it as a flyback converter. In fact, this dot point, what does it show? We are seeing any transform. This dot point is very important. If this is reversed, whole game is reversed. Nothing will work. So this dot point is is not only to showcase something. It is from technical design requirement point of view. Is that it is nothing but it shows the start winding of a transformer, right? Transformer or inductor, from which end have we started the winding, right? So that has to be shown. So whenever we are designing a flyback converter, so during the layouting on a PCB or something else, this connections has to be ensured. Reason behind that, all other converters transfers the energy when they are switching on. Okay? But in this converter, this is one converter which transfers the energy when the switches are off.
What will happen if the dots are on same side? Dots starting winding. That dot on same side means on starting points. On same side, opposite to that one.
That's all. When it is, this is positive, on that side, this will be positive. Positive, this will be negative.
At this point, that the starting winding is on same line.
This one?
That is one. That opposite to that.
See, whenever switch is on, right? On that time, this behaves like a, what will happen? The current starts going through this winding, right? And it's stored there. Right? This one will be 0, this will be high. Correct? When it is on. And when it is off, on that time, what will happen? The stored energy is transferred to this side. And how will it go? This is on the, when it was on, it was high, and high is this. So this is 0 point here. So no energy has been transferred. When switch is off, on that time, the stored energy, whatever it was there, this has been positive. This section has been positive, and then it is transferred. In the inductor, when we see the functionality of an inductor, how does it work? For a moment when current flows through it, on that time it will not transfer energy. It will store. Whenever it has been left for the off condition, on that time it transfers the energy. And it is reverse bias. This polarity is reversed for an inductor. When it is off, then this will be positive, this will be negative. As long as this switch is off, the same thing, this will be positive, this will be negative because this energy has been stored here, right? And see, this has been positive as a polarity point of view, this will be positive. And this is negative, that's why this will be negative. So in off cycle, when it is positive, then this diode is forward biased and it will transfer the energy.
Means that output polarity is going to be changed.
Yeah, in inductor. That's the thought. The objective is that flyback converter, flyback transformer is not transformer. It is inductor. Key things, the takeaway here, we are calling it as a transformer, but it's not transformer. Its function is like an inductor. That's why whenever we design the flyback transformer, in transformer we leave a gap in the code. Correct? What is there? Okay. Normally, whichever transformer is there, gap is not provided in the gap in the code. There are the two goals. We can say, suppose something key code is there, right? for transformer. In transformers design, there will not be any gap between the cores. That is point. But at the same time, where we are going for inductor design, we are using the same core just for understanding. On that time, we have to apply some gap here. Why? This gap is mandatory to provide some gap to avoid the saturation, to enter that inductor into the saturation. And we, in terms of magnetics, when we say saturation, means property has been changed to resistive, not magnetics. Okay? So, in the same way, there is a formula, just one thing. For the flux density saturation, flux density of a core is equal to be somewhere n into IAC IDC minus IAC upon L upon Ln upon V minus M. Something. So this is Lg what we have mentioned. This is gap length. And this Ln is the magnetic path length. Whenever we see the data sheet of a core, there we see magnetic path length is how much there, permeability is how much there. On that we have to solve a design. So magnetic flux density is another area, just because of limitation of time, I am not able to share that. I am not able to discuss here. So this gap, in case this has been 0, this is Lm actually here, this is Lg. Right? So just because of if Lg becomes 0, so what will happen? Core will get saturated. So that's why in inductor it's mandatory to provide some gap. Some gap means it's as per calculation. How much? It's 1 and 1.5 like that. What is that? So it will increase its VH curve. VH curve you see, right? So VH curve is expanded. Like that point is given for that.
Flux density in this situation.
It's increase now. Whenever gap is provided, flux density, operating flux density will be expanded. It will increase for the inductor. That is objective gap. Okay. So for this private transformer also we provide gap. Any transformer designed for a private converter will have a gap. How much gap? By the calculation we have to see how much flux density we want to use, what is the turns ratio and all, how much voltage is moving. According to that, whatever the minimum gap is needed from the calculation it comes and then much only is provided. So from action point of view, fly-by transformer is an inductor instead of transformer. Practical challenges. I think this is the last slide. Okay. During once our designs are done or something like that, or during the design phases, these are a few key things where we face the challenges, like EMC comparison. So EMC, this is all against the as per provided test standards, where it's C, conducted emission, conducted radiation, conducted emission, conducted susceptibility, radiated emission, radiated susceptibility, what we call immunity test. Means something is coming to the system, should not impact this. Our system should not impact to others also. That is what I mean that. So to comply the C testing, EMC filter is highly important to be used. It should comply. That is only that which brings the noise below the standard guidelines, right? Then things come for HV, high voltage testing, impulse testing, something 500 kV, high kV is being fed to that, nothing should happen to the system. From this, whatever the scenarios applicable in the environment, during the lightning, we see number of surges come, right? That is simulated just because of by this testing. So, few examples are given: RE, RS, CS. RE, that is radiated emission, radiated susceptibility, conductive susceptibility, that is that. Transient response problem, voltage and current, load and line regulations, voltage and current network, voltage and current stability, thermal management with respect to power density, power dissipation. Questions, please.
How to improve the battery life of the battery for the EVs? Life of the battery.
Life of the battery, how to increase. This is again in the code of battery designers, manufacturers, right? So, in fact, if you are asking this question with respect to the battery, whichever has been used, which is supposed to be used in our design, suppose then how can we take a maximum battery life of that? That is in fact by making this battery management system. What we call battery management system, the purpose of BMS is nothing but this is only how to get the maximum battery life in that. For example, in battery management system, what happens? In ideal condition, wherever the consumption is needed only that much consumption is to be taken. Not every time full current has to be drawn from there. In ideal condition, it should be standby current is to be there. So that wherever it is needed, on that time, maximum utilization is again occurring, and then battery life will be taken. So battery life, BMS objective is to increase battery life of it. And that is all as per the applications, in what conditions, how much current is to be taken. Right? That is one. That is what with available battery, how much we can use the maximum battery life in our design. That is one thing. Second, from designer side, who is designing there anyways, evolving the technologies. How right now I think for 5 years is the maximum battery life from manufacturer side. Rest of the things this is still being evolved to increase this. So why not 20 years? Why not 15 years? Right? Hope I answered the question. Anybody else, please?
Insightful on sustainability technologies developed by all electronics and its applications. And truly, today's morning session was truly a good example of industry institute connect. Provided so much of knowledge. May now request Professor Ramya to come up here and hand over a small token of memento with our appreciations and the same.
Okay, thanks a lot everyone for having me. By the way, anytime if you want any discussions on these technical things, so my number is available. Anytime can discuss with me on that. Right? Thank you.
I think we have delayed, we don't have time for reflective journal. We'll go for lunch now. Please come back 1:45. Immediately we'll have reflective journal write up, then MCQs,